Dr. Ryan Glasser's group. So today I'd like to talk to you about seeded and unseeded four-output four-wave mixing. So I'm basically about to have the same slide that Thomas had a minute ago. So this is a refresher to everyone. This is a coherent state of light, unsqueezed state of light, classical light beam, or rather the electric field in time. And then on the right, we have a phase-space picture of the same thing. So you can ignore the axes labels, but what you need to know is the distance from the origin in this, what we call a ball and stick diagram, corresponds to the amplitude of the coherent state, or amplitude of the electric field rather, and its rotation in polar coordinates corresponds to its phase. So what you'll notice here is that this has some distribution. It's not just a point in phase space, but it's some ball. And that's necessary due to the uncertainty principle. Also, when you have classical light, when you have like a coherent state of light, this distribution is necessarily circularly symmetric. However, when we go into the quantum regime, as he mentioned, we can have squeezed light. Here's two examples of squeezed light, amplitude squeezing, where we know a lot about the amplitude quadrature of the light. And you can see that here, maybe. We know a lot more about the amplitude at the expense of phase information, and then vice versa with phase squeezing. So here's just to show that this can be used for many things, notably in interferometers like LIGO. It can help improve sensitivity a notable amount. If you input squeeze light into the port of an interferometer. The type of squeezing we work with in our lab is a little bit different. We use two-mode squeezing. What you just saw is single-mode squeezing. In this case, in the two-mode case, the quantity that's actually squeezed is a linear combination of quadratures of two fields, or twin beams as we call them. So here we have diagrams of some simple crystals. Using parametric down conversion, people can create single mode and two mode squeeze vacuum, or squeeze light. Ours is not crystals. I'll talk about it in a second. And here's what the quadratures would look like. We have X and P of modes A and B. And we have two mode vacuum and then two mode squeeze vacuum, where vacuum just indicates that the distance from the origin, the average distance from the origin is 0. The method we use is called four-way mixing. This is a third-order nonlinear process, and this creates two twin beams, as I mentioned. This process involves two photons, which we call pump beam photons, being annihilated in a medium, specifically rubidium-85, and then we get two generated modes at two different frequencies and also two different spatial locations. We usually call those probe and conjugate, but people call them signal and idler, and so on. As I mentioned, these are quantum correlated twin beams, and we get two-mode squeezing or intensity difference squeezing. That's measured on a spectrum analyzer up here. So we take two detectors and then do probe minus conjugate, and we find that the noise level of that signal when it's squeezed is below shot noise. So below what's classically allowed. This process, this four-way mixing process, can either be seeded, as shown here, with a weak probe beam before the cell, or unseeded. In the unseeded case, the seed is provided by vacuum fluctuations, so the overall output, the overall generated probe and conjugate is much less bright. There's also, in the unseeded case, no spatial selection. So instead of two beams, we actually get a hollow cone about the pump beam. And I'll show you a picture of that right now. So this is what we do. This is unseeded four-way mixing when we have the right cell temperature and the right pump frequency. Just input a pump beam into the vapor cell. We get this hollow cone, and if we look at it on a screen, we see a ring about the leftover pump beam. What we've done is we've put in a second pump at a small angle to that first pump. Same frequency, same power, and all of that. So one might expect to get these two rings in sort of a Venn diagram shape. But we know that that's not what happens, that there is some spatial collapse when we put the second pump in. So knowing that, a good guess, and the guess we made, might be that you get a spatial collapse at those two overlap points of the Venn diagram. Going forward with this assumption, if we have a spot here, we know that one's going to form here from just the single regular Fourier mixing interaction that we're used to, because this is phase matched. If we have a probe here, it's going to create conjugate here. If we have conjugate here, it's going to create a probe here. Likewise with the bottom one, and it's symmetric, so the same thing happens on the other side. And this makes a lot of sense. This is what we guessed would happen. We guessed we would see this 6-mode output if we just put 2 crossing pumps in. And ostensibly this group did too in 2017. They just went right ahead at a low cell temperature and seeded at location A1, and they successfully did get this 6-mode output. It is phase matched, it's legal, it makes sense. They were able to find squeezing between different combinations of these output modes as well. But what's interesting is that is not at all what we found when we look at the unseeded high temperature case. So it seems like what naturally wants to form is always this 4-mode output, where there's 2 modes above and 2 directly below the pump beams. And this happens at a wide range of pump angles, small pump angles, temperatures, powers, frequency, and so on. It never really forms that 6-mode output. So that was a little unexpected. Here's just a picture of what that looks like on our screen or on our CCD camera, where I've subtracted out the leftover pump beams in the center after the fact. We have pump A only, pump B only are both rings, and then pumps A and B together create this 4-mode output. Here's just a look at the shift from the single ring to the 4-mode case, and back when we change the ratio of pumps A to B. You can see that the overall image intensity, pumps are subtracted out, the overall image intensity is much less bright actually for this 2-mode case, even though you're putting in the same amount of pump light and everything else is the same. Which is kind of interesting, makes it kind of interesting that it forms at all in the first place. So maybe something that will give us some insight into that, maybe not, is looking at the sort of toy interaction Hamiltonian. Here we have, if you look at just the first term, we have the standard Hamiltonian that we use for thinking about simple Fourier mixing that we're used to. So just looking at pump A and looking at modes 1 and 4, we get this first term here. Then we just extrapolate and don't make any assumptions about the interaction strengths, the epsilons, between the different modes. The only assumption that we've made here is the standard one, that we have an undepleted and classical pump beam, or pump beams in this case. Then what we can do is simplify. This is obviously a typo here. That should be a dagger 2. We realize that if everything is balanced, if we have 2 equal pump beams in size and shape and frequency and everything, we can really categorize it into 2 different interaction strengths, single and double. So that's epsilon S and epsilon D. And I've shown them in the diagram here by light and dark blue respectively. This is pretty much the first example of this dual pump Fourier mixing process shown in this manner. And what you'll notice if you examine this is that every single mode, maybe this is obvious too even without examining it, but every single mode, 1 through 4, experiences the exact same process. So each mode is correlated to one other via the single mode Fourier mixing process and another via the dual mode Fourier mixing process. So we've changed some experimental parameters and looked at things like how the intensity changes. This one's a little bit interesting. We looked at the intensity of the output at certain spots as we increase the power of pump B. So for the blue curve, we looked at somewhere on this ring, and we see that it goes down as you increase pump B, which makes sense because the 4 spots form. And for the red curve, we looked at spot 2 only. And we see that it increases as expected, but it does have this little dip before increasing again. So we don't really have an explanation for that. However, temperature makes a lot of sense. We're not seeing any shifts or anything that we don't understand beyond just the fact that the overall intensity is much less bright, even though we have double the power going in. We do see a shift when we look at the pump detuning from the absorption line in rubidium 85. When we plot this as a function of the power of pump A, we see that it has a linear trend, which is characteristic of an AC Stark shift. So that's pretty much expected when you have this extra electric field in the cell shifting the atomic levels. So in summary for this paper, we demonstrated this 4-mode optical stability that's pretty robust and stable and balanced using a new phase match forward mixing configuration with 2 crossing pump beams. In this case, each photon is correlated to exactly 2 others, and it's unseeded, so you don't need any frequency modulation, you don't need any AOMs or EOMs, and you don't need to align any probe beams. This balanced output, this 4-mode output, suggests that this configuration is going to exhibit the strongest degree of quantum correlations in experiments with 2 crossing pumps. The fact that it happens without a seed sort of suggests that. And we think that these results might be applied to multi-party entanglement distribution, as in this paper, where they just looked at the ring about a single pump beam, and they generated pairs of correlated random bit streams for secure key distribution. So our setup would be more readily applied to maybe like a 4-party network. If you're interested, there's a lot more in the paper. And I'll talk about what we're currently working on. So my colleagues can tell you a lot more about this, but they're working on the 3-mode case. They're behind me, I like to think. They are looking at things like, this is all theoretical, all in like Mathematica and MATLAB. Looking at the noise factor, as you increase squeezing parameters like R1 and R2, which can be things like power, frequency, temperature, and so on. I think something that's interesting that they've found is that if you sit at a constant R1 and increase R2, so you might be increasing the power of the second pump beam, you can go from having no squeezing, where you have a positive number here, get squeezing, and then as you keep increasing that power, you go to a region of no squeezing again. And I think we figured out that that's in a regime that we can't really get to in lab, but I still think it's pretty interesting. Yeah, there's a lot more of that. So what I'm currently doing in lab is seeding that 4-mode output configuration, where I've aligned 2 pump beams in, set up an AOM, shifted the frequency, and put them in at a small angle corresponding to the angle at which they formed in the unseeded case. Just like the single ring about a single pump, this configuration is brighter than the unseeded case. The only difference is that the seeded and unseeded case, in this case, look exactly the same spatially, whereas in the ring case, it goes from a ring to 2 spots. So, I know I changed around the labels just to confuse you. What we've done is we've noticed that this output, when you seed it, sort of wobbles around a lot. It's not balanced like in the unseeded case. So we suspected that it might be phase sensitive to the difference in phase between the 2 input probe beams, the 2 seed beams. And what we've done to quantify that is we put a piezoelectric mirror on one of the probes, one of the input probes before the cell, put a sine wave on that from an arbitrary waveform generator, and then looked with a detector at conjugate B, the generated mode after the cell. So this is what we see when we look at that detector, when we either have only probe A seeded or only probe B seeded, and we see that there's not really any signature of that sine wave. But then when we turn them both on, we get a clear 100 hertz response. And it's interesting here that the average maybe of this blue signal is higher than either of the two single seed cases, but the minimum does go lower than the probe B only case. So it's kind of variably a phase sensitive amplifier and de-amplifier in that way. Here's a look at that as we change the power ratio between the two probes. So on either end, we have all one or all of the other. And at the very center, this is the variance in conjugate B. We have the highest variance. This is a look at the same thing, the variance once again, but with probe detuning from the pump beam. And we can see that there is some optimum if you want to look at it that way. So why is phase sensitivity important or interesting? Why is it interesting that we have this? Well, as we mentioned, squeeze states injected into the ports of a beam splitter in an interferometer, like in LIGO, lead to improved sensitivity. The question, sort of maybe raised in the 80s, but there's a big resurgence in this now, is why not combine the squeezing generation and the interferometry process into one? So this is a little bit backwards here, but here's a figure of a standard interferometer. This is a Mach-Zehnder interferometer that you're probably very used to. This is what we call an SU2 interferometer. Then what an SU11 interferometer is, or a nonlinear interferometer, is the same exact thing, but you've replaced the beam splitters with parametric amplifiers, or whatever, crystals, vapor cells, something that generates this nonlinear squeezing process. And you can see here that this group, this is an experimental result, they were able to get over 4 dB of increased sensitivity in their phase detection. So SU11 interferometers are really interesting. In 2018, last year, the LET group pointed out that you don't actually need 2 parametric amplifiers, you don't need 2 vapor cells to get the same response. So I'm sure everyone felt very silly for putting 2 in. But it's important to note that you do need Homodyne detectors on the end to read out the phase difference when you use a truncated interferometer. So that's a difference between, if ours does work to be a SU11 interferometer, ours does not need Homodyne detectors, and you can read out the phase information just with direct intensity detection.
Sorry, why is it that you can eliminate the second NLO? I didn't quite catch that. And have the same performance?
You would have to read this paper.
All right.
Yeah. Yeah, they published it last year. Yeah.
Do they only see one of the, in this paper, do they see both equal or just see one?
This is vacuum.
That's that.
Oh, yeah, this is vacuum too.
So,
But they have to do Homodyne detection on the ends.
you still need a homodyne on the vacuum output also? On the output that corresponds to the vacuum?
Yeah, like the conjugate, the generated mode.
You still need, what would the LO be on that? The local oscillator would just be?
I think you have to
Or would you?
use an AOM and get another local
Oh.
oscillator at that frequency.
Okay.
Yeah. Or not use chord mixing, I guess, would be easier. But yeah, they showed that you get exactly the same limit of the improved sensitivity.
I think maybe a reason for it is that the NLO is a Gaussian operation, right? And so is the Homodyne detection. And so I think you can, based on these measurement outcomes, you can you can effectively apply what that NLO would have done to the classical measurement outcomes, and I guess you need this lambda gain factor as well to sort of compensate for what the NLO is doing. That would be my guess. That you can
Yeah.
somehow incorporate in the post-processing.
Something that they're glossing over in this paper is that this is not really necessary at all in a regular nonlinear SU11 interferometer. So yeah, you're totally right that it does. It's more like you're replacing this with the Homodyne detection and maybe also the gain in order to get a truncated interferometer. You can't truly just chop the experiment in half and get the same result.
Yeah. Okay.
But it's useful if, for some reason you don't want two cascading cells.
Well, the second experiment is much easier to do, right?
Right, totally, yeah. Depending, yeah. So another reason that phase sensitivity is interesting in an experiment like this is that phase-sensitive amplifiers are the only known optical amplifiers that can provably achieve 0 dB amplification, noiseless amplification. So the signal-to-noise ratio of the input is the same as the signal-to-noise ratio of the output, even though you're increasing signal, which seems like magic. If you have noiseless or near noiseless phase-sensitive amplifiers, it's been shown that you can improve continuous variable quantum key distribution protocols even when you have inaccurate detectors or loss near the detectors. And also a phase-sensitive amplifier before the detector in homodyne detection can increase that efficiency to be perfect. So it's very useful if we can show that this is noiseless. So if it is, I'm kind of presenting this in the middle of this experiment, so it's a bit of an awkward time, but if we can show that it is noiseless or less noisy than a phase-insensitive amplifier, we have an advantage over other methods of getting those because we only use one cell, as I mentioned. There's no cascading. In my diagram here, I've put 2 beam splitters in, but it's important to note that those are not at all necessary for any interferometry we're going to do or for the phase sensitivity at all, or the amplification. They're just to make this small angle alignment easier. So that's not vital to the experiment. We only need 2 input frequencies. There's a lot of experiments like this that use cascaded cells or 3 input frequencies. So in our case, we only need to use 1 laser and 1 AOM, less costly and less difficult to align. And finally, we don't have to do any homodyning, like I mentioned, with the truncated case. So going forward, as I said, we definitely want to explore the noise factor of our 4-mode output when it's seeded. We're sort of in the middle of this, but we want to seed this 4-mode output seed the dual pump configuration with different seeds at different angles, such that we get 2 modes, like everyone's used to, 3 modes, like in the theory that Wenley and Sarah are doing, 4 modes, like I just talked about, or 6 modes as in this paper, where they got squeezing between the 6 modes. And we want to sort of verify that the 4-mode case is optimal for a reason, or that it naturally forms for a reason, and maybe has better quantum correlations, or at least more balanced ones. Finally, this system can be applied readily to a 4-party quantum network, if you think about it. So there's no reason that we can't add more pumps or more complex 4 mixing geometries to increase the dimensionality for the parties in this network. All right, so I'd like to thank my group, Anissa, Board of Regents. Thank you. Questions?
The last book you have shown, if I collect the 4 output modes and I post-select on 4 photons, do I get an entanglement state?